Good day. For those of you who do not know us, we are the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss wild pointers. So in this topic, we will define wild pointers. We will see how wild pointers cause problems, and sometimes you're lucky, other times you're not. We will review the steps for avoiding wild pointers. Now, uninitialized local variables can cause problems, which is why we insist you always initialize them. However, when those local variables are pointers, it's much worse. An uninitialized pointer is described as a wild pointer. The term wild is used because we have no idea what its value is. The most significant issue is with cross-platform development. Suppose you declare this variable to be a pointer on a Windows platform. If you were to run this code over and over again, the default value it is assigned is the 0 address. This is the value of null pointer. So it's not a problem because that is the default value. This is because Windows clears memory before it gives it to you. If you were to compile the same code on Linux, all of a sudden it has a different value, a completely random value, because essentially the operating system is just giving you the memory and you get whatever is there. All right, consider this code. Here inside the main function, we just print to the screen that we are currently in main. We will then call the function f. Now, f has an uninitialized local variable that is a pointer. So now in f, I will print the value of that local variable. Next, I will attempt to assign to that address. When we execute this program, here's the output. We get a wild pointer, an address that makes absolutely no sense, and then when we try to assign to that address, we get a segmentation fault core dump. Segmentation fault because you tried, or this program tried, to access a memory location it was not authorized to do so. So you attempted to access a segment of memory which was not allocated to your program, hence the program terminated your function, period. To reiterate, whatever memory is at that location, it is almost certainly not assigned to your program, and so when you try to access it, the operating system will terminate your program. Your program is not authorized to access any memory that was not explicitly allocated to it by the operating system. Now, with wild pointers, sometimes you're not so lucky. Here we're going to have a program where main simply calls two functions. The first, init, will initialize its local variables even if they're pointers. The second, noInit, will not initialize its pointer local variables. Let's look at these two functions. Now, init is going to have a local variable, and it is initialized with a call to new. So, memory has been allocated for an int, and that memory has been initialized with the value 42. Now, we're going to use this particular local variable, and then at the end, we're going to clean up that memory. We're going to tell the operating system we don't need it anymore. And so you may think, well, p_value is going out of scope immediately as soon as this function exits. So why bother setting p_value to null pointer? The local variable is gone anyway. Well, immediately after we call init, we will call noInit. Now this has a local variable that is a pointer. However, it's not initialized. we're going to print out its address, and then we will try to assign to that memory location. And we'll see what happens. Well, executing this program, inside of init, there's the address that was returned from new and assigned to p_value. When we immediately called noInit, immediately after having called init, it happens that the local variable p_local is in exactly the same location as the p_value. Consequently, that address that was assigned to p_value is now sitting there in the location for p_local. Now, you may wonder, why is this not crashing? Because the operating system is lazy. Just because you deallocated some memory, the operating system doesn't necessarily immediately revoke your ownership of that memory. It has the option in the future of doing so, but sometimes it's just cheaper to say, well, okay, yes, I'll flag this as deallocated, but I'll still keep this within the scope of your program just in case you ask for more memory in the future, which is not actually a bad idea. However, in this case, it means that we are still able to assign to that memory. That is, unless between the call to init and noInit, the operating system decides it needs that memory for something else. That may be 1 in a million times. So let's reiterate why this code executed and seemed to work. In the first function, the local variable was indeed assigned new memory allocated to it by the operating system. At the end of the function, the memory was deallocated but not reset to null pointer. After all, the variable p_value is immediately going out of scope. The operating system, however, is relatively lazy. After all, the operating system should not do more work than it has to. And so consequently, it left that memory allocated to this executing program, as, after all, the program may at some point in the future request additional memory. It's easier to reallocate memory than it is to find new memory. In the second, the local variable happened to occupy the same location on the call stack as the original. It was not initialized, so it takes on whatever value happened to be there. Now, if you're lucky, it's going to be garbage. However, in this case, the program was unlucky. What was there happened to actually be at one point a valid address. So this is the value that it takes on. Now, the unfortunate issue here is that if this function was to continue using this memory location, probably 999,999 times out of a million, it's going to work. However, there's a 1 in a million chance that between those two function calls, the operating system decides, oh, I need this memory for some other request. In which case, that memory is no longer allocated to your program and your program will crash. This can cause some very difficult to find bugs. All right, how to avoid a wild pointer. First of all, always initialize all pointers, even if it is to null pointer. Now, the default value is null pointer, but you may want to be explicit about that. Benefit. If you ever try to assign to memory location 0, the operating system will terminate your program, guaranteed. So if you have an issue the operating system will make sure you're aware of it. Also, when memory is being deallocated, always set the pointer to null pointer even if that local variable is immediately going out of scope. Alright, to summarize, following this topic, you now understand that wild pointers are uninitialized pointers. You understand that accessing wild pointers will result in one of two possible consequences. The operating system may terminate your program as you are trying to access memory you do not have access to. Alternatively, you may use memory that has been allocated to you for some other purpose. Understand that the first one is easy to track down because there was a crash. The second, if a problem does arise, and it may be very seldom, it may be difficult or almost impossible to track down. So you now know that you should always initialize all pointers, and even if nothing else, initialize them to the null pointer. And you know that you must set all local variables to null pointer after any deallocation. Here's the references, the colophon, and a disclaimer. Cheers!